All right, well, thank you. It's good to be here. So I'm going to talk about a problem about rearrangements of Fourier series, but I want to put this into a more general context. I work on some problems in harmonic analysis, some problems in combinatorics, some problems in number theory, and some problems in theoretical computer science. And I want to talk about three problems that all fall under the same framework, one of which is what the title is on. And so maybe a more general sort of title or theme of this talk is going to be on the distribution of values of orthogonal systems with restricted supports. So I'll try to convince you that this is a worthwhile thing to study as I go. And so let's just remind you what an orthonormal system is. So this is just a set of n. There's infinite. They can be infinite, but here for most of the talk I'm going to care about finite orthonormal systems. So n complex valued functions on some probability space that I'm just going to write as t. And then if I take the inner product of any two that are the same, I get 1. If I take the inner product of any two that are different, I get 0. So this is very, very basic. And so the meta question that we'd like to understand is if I just have a system of size n, and I take some sort of subset of n, and I consider omega is indexing some subset of these basis of these functions, I would like to know what can I say about a function whose sort of Fourier, or whose function that I get by just putting coefficients on this subset of the system. So this is the general theme of the kinds of problems I'm interested in. And so there's two different regimes in which you can work in. One is a random situation where you try to consider some sort of random object. And generally, in that case, you can prove much, much more than you can prove versus an explicit case where you're trying to actually find an explicit example of one of these objects. So in the random case, you can prove sharp or very nearly sharp results. And the proof techniques tend to rely on stochastic processes and metrical entropy and things like that. Where on the explicit side, typically you're working with a subset of the trigonometric system in this case, and you basically do a lot of work to beat trivial estimates, to marginally beat trivial estimates. And here you need to choose from analytic number theory, such as the circle method, combinatorics, such as some product methods, Fourier restriction theory. And then it seems like people have sort of thinks that ABC conjecture, polynomial Feynman-Ruger conjecture, and Falting's theorem, and things like this is what tools you need to go further. So it seems like in the explicit regime, the things are very, very difficult. And so I want to talk about three problems of this form that have sort of different flavors to them. So I guess before I get to that, so so Bourgain has a very sharp result on the distribution of values in a random subset of a given size. I don't want to say too much about this, but he has basically a very sharp result. It says if you take a subset of an orthonormal system of a given size, then you can get an LP to L2 estimate that is sharp in the sense that you couldn't hope for anything better for a set of your given size. And the construction is random. He randomly constructs a subset of a given size. But if you go ask in the explicit regime for an explicit set with these properties, basically nothing is known. So the first problem of this flavor that I want to talk about is finite field restriction estimates. And so here I'm going to work with an orthonormal system, which is just going to be the set of characters so FP is just going to be the finite field of order P, and the 3 means that I'm just taking the Cartesian product with it 3 times, and I have characters on this group, and I'm going to define a subset of these characters that correspond to the paraboloid. So this is just this set where I take it where I basically let the first 2 coordinates range over everything, and the third coordinate is the sum of the 2 squares of the first 2 coordinates. So the entire set has size f cubed, and this subset has size f squared. And then so I associate to this paraboloid a set of characters. And then what you would like to do is you would like to prove an LP inequality of the following form. You'd like to prove that the LP norm of any function, so I allow these ANs to be arbitrary, but of course I have an L2 norm of them over here, and I would like to prove an LP inequality of this form right here. And so the conjecture is that when p is greater than or equal to 3, and -1 is not a square because the arithmetic of the field presents, so the problem has a different flavor if -1 is not a square versus is a square, and I don't want to.
There's a problem with p is used both for the prime and the norm.
Yes, so that's a problem, but hopefully you can parse that. Yes. I'm sorry? Oh, right. So I'm gonna do a normalized counting measure on the. So I'm gonna put. So I need to put a measure on here, right? And so I'm gonna do 1 over f cubed. So that will make these orthogonal. Right. Right. So there's a lot of definitions when you want to precisely state these things I was trying to avoid. And so the conjecture is that when p is greater than 3, then this is true. I can, so this is a conjecture of Mach and Hopton tau, and so
Which p?
the exponent. Yes. So the idea is you want this to be uniform in the field, but I mean I have a factor of the field right here. And so let me just sort of give you some slight. So there's two motivations for this problem. One motivation is that there's a restriction conjecture in Euclidean harmonic analysis, which this is a finite field model for, which is one of the motivations for it. I mean, another way of looking at this is, we've spent a lot of the past century trying to detect cancellation in exponential sums. And typically you have something where you have like e to the n, e to the some polynomial, and you want to prove that this is small. But what we're trying to do here is I'm taking an exponential sum, which is supported on some sort of set that is somewhat small, and then I want to prove that there's a lot of cancellation in this exponential sum for arbitrary coefficients. So that's another way of looking at this. And so currently we can prove this for about something slightly less than 3.6, and the conjecture is 3. So there's still a ways to go. But this fits into this idea of that we have this orthonormal system, and we say that we're looking at some sort of subset of it, and we're trying to figure out the distributional properties of functions that can be supported, whose Fourier support is on this subset. So let me talk about a different problem of the same flavor, and so this is the compressed sensing problem. And so here you have an orthonormal system on some set that's just indexed by, so n bracket is just 1 through n. And if I take a function supported on this, and I sum over and I sum x over all the entire space, well then this is just equal to the sum of the squares of the coefficients. This is just parsable. This is quite easy to prove. And so if I take a subset of 1 through n, then what I would like to do is I would like to say that if I sum over just this subset, then that this is approximately equal to the appropriate the L2 the sum of the squares of the coefficients times an appropriate normalization factor. So if this is somewhat of a random set and the AIs are fixed, you would expect this to be true, because I've sort of just normalized by the appropriate factor to account for the fact that I'm only summing over a subportion of the.
What's the y there?
Yeah, so it should be x. X and y should be the same. It's a typo. And so this is what you sort of expect if you fix the coefficients and you chose omega randomly. And so there's a very nice theorem of Candace Tau and Ruelson-Verschenen that says that if you take if I take an orthonormal system on a set of size n, and I look at coefficients whose support, so I just use a0 to mean the support of A, is size r, well then this quantity right here where I sum only over the elements in some omega is actually upper and lower bounded by what I would expect it to be, as long as omega is bigger than r to the log to the 1/4 over epsilon squared. And so, I mean, if you think about this for a little while, you'll think that I need to have at least an r in the log n here, and that the epsilon 1 over epsilon squared is also sharp. But here there's an interesting open problem of reducing this logarithmic factor. So originally Candace and Tau proved this with a log to the 6 right here, and then Ruelson and Verschenen currently have log to the log to the fourth, and it seems that the correct answer should be r log n over r. But that is open. But this is an example of where you're trying to understand the distributional properties of subsets on a sort of a general orthonormal system, and this has applied applications. Capital, yeah, they should be the same. Yeah. Yes. And so then I'll get to the third problem in this area, which seems to be somewhat different, but is also quite nice. And this is about rearrangements of Fourier series. So if I give you so now I'm going to give you an infinite orthonormal system. I'm always going to assume that the orthonormal systems are bounded in this talk. And so I can write a function, say, has an expansion with respect to this orthonormal system. And so a natural question to ask is, if I just take the limit of the partial sums of this of the Fourier system, the Fourier expansion of this function, does this converge to the function? And you can only hope for this to be true almost everywhere. And you could ask if this is true almost everywhere. So you know, in the case of if this is the trigonometric system, then it's a very deep and famous theorem of Carlson that this actually does converge to the function almost everywhere if the coefficients are in L2. But this is a fact that's very specific to the ordering of the trigonometric system. So the trigonometric system gets an ordering from the integers, and this is very specific to that ordering, and it's in fact known and is back to the 1920s that you can reorder the trigonometric system in a bad ordering such that almost everywhere convergence fails for functions in L2. So in the 1920s, Kolmogorov asked, well, if I just give you an arbitrary orthonormal system, I know that this may not hold for all functions in the system, but perhaps I can reorder the system so that for every function in the system, I have almost everywhere convergence. And so this is a question of Kolmogorov, and he asked in the 1920s in his open. But you'll see that this falls into the same framework is the theme of this talk. And so if I give you an orthonormal system and I give you a function in the span of the orthonormal system, then I can form an associated maximal operator. And typically questions about almost everywhere convergence are addressed by studying maximal operators. And so there's a Rademacher-Metschoff theorem that says that if this is a finite orthonormal system of length n, then I can actually upper bound the maximal operator by the L2 norm of the coefficients times log n. And this log n is known to be sharp, that you cannot reduce this log n for a general orthonormal system. But then you could ask, well, maybe I can reorder. If I take a finite section of an orthonormal system and perhaps I can reorder it such that I can reduce or eliminate this log n. And so if you could actually eliminate the log n in this, it would actually imply a positive answer to Kolmogorov's problem. And so there's some partial results along these lines due to Bourgain in the 1980s, and he showed that you can reorder the system such that the maximal operator associated to the reordering satisfies a log n bound. So you do get an improvement, but this falls short of resolving Kolmogorov's question. And so let me just quickly explain why this fits into this sort of framework I was discussing before. And so you have this maximal operator associated to a rearrangement. And so if you want to analyze the distributional properties of this maximal operator, what you really need to do is you need to understand the distributional properties of functions who are, so if I just take some subinterval, I need to do this for all subintervals, and I want to understand how big this quantity can be. So just the coefficients in the orthonormal system elements on a particular subinterval. Well, so this is just rewritten in a slightly different way, where this is omega. Well, if I chose my rearrangement to be random, well, this is roughly the same as just saying that this set omega right here is random associated to this interval. And so this way, so then again you get down to these questions of I have an orthonormal system, I'm choosing a random subset of a given size, and I'm looking at functions supported whose Fourier coefficients are supported on that set, and I want to understand the distributional properties of it. And so this is, and so then you can sort of use tools in this theory to address these questions about rearrangements of Fourier series. So this is So I hope this was short, but I hope there's this under this general theme showed 3 different problems that all sort of that seem to be of a different nature, that all sort of relate to understanding the distribution of values of sort of orthonormal systems with restricted elements. And so that is the conclusion of my.
Thank you very much.